Good morning, Geometry. How are you guys? We're going to do a section here. It's section 5 of chapter 11. And I have to say, I'm not sure enough time is devoted to this in this book, but I'm going to go with it like it is and we'll see how it goes, okay? You know that classical geometry was started by Euclid. We talked about that way back when. Greek guy walking around in his toga came up with geometry, wrote a bunch of theorems and postulates and corollaries, and that's what we've been studying really up to this point. Likewise, geometry unfolded for hundreds of years until a few thinkers started kind of challenging the rules. A few nonconformists. They didn't want to just go with thinking of geometry like it's in a flat space. They started kind of imagining if you lived on a sphere, like a basketball. Wouldn't that be fun if you lived on a basketball? And traditionally we talk about a line as a distance between 2 points, right? And that's it's straight. Because we're thinking of space and the world we work in, the grid we have as a kind of a 2 or 3 dimensional thing. Well, 2-dimensional, kind of flat like that. But if you think about it, if we have a point here and a point here, well, you can see that if you lived on top of this basketball and that was your entire reality, the distance between those 2 points is not going to be a straight line. Can you see that? It's going to be this curve here. And, likewise, they just started challenging all these things. We think of a triangle as 3 points and then straight lines in between them. But if you had 3 points here, I can't quite do it for you. Can you imagine this? But you can imagine that between my 2 fingers and this pen, those are not going to be straight lines anymore. So a triangle no longer has straight edges. Anyway, suffice it to say that you can imagine the upheaval that went on in mathematics when people started proposing non-Euclidean geometry. It had its own set of theorems. And depending on whether it was like a sphere like this, or you also can do non-Euclidean geometry. I don't know if I can show you this, but like pretend it's like almost like a saddle. So now think about if you had a point here and a point here, that is not going to be a straight line in between. Anyway, you can imagine all kinds of curved up spaces, and Euclid's rules are not going to hold anymore. And in fact, in I think it's 1912 or whenever Einstein came up with the theory of relativity, the theory of general relativity, especially when he talked about gravity, he started imagining what if space around us was not flat like we imagine it. And that's when he needed, because it was beyond his math really to deal with the non-Euclidean geometry. So he had to go to get some help with this. But in fact, that's how we think of space now, is the time-space fabric is not flat. It is curved up, and gravity causes it to bend and warp. So anyway, it's quite an interesting subject. It's really beyond me. I'm not sure I can teach you very much about it, but I can give you a concept of, I guess, what they're talking about. They show you a few pictures in your book, and that might help you kind of figure this out. One of the greatest applications of this is, let me just draw the United States. Oh boy, that's really bad. Let me try it again. The United States, and then, Europe over here, and then Asia over here. So, okay, obviously the United States, look at that. You can see Florida down there. You can see Washington. And then let's say this is Europe and that's Asia. Well, when we look at it on a flat map, it seems like the fastest way between here and there would just be a straight line, right? But you'll notice if you ever go on a plane flight, that's not the way that they take you. And it seems very strange. But that's because the globe is a curved space. And the fastest way between 2 points on that curved space is actually taking the great circle of that globe. And so oftentimes you'll start in one place and it seems like we want to go over here, but we actually go up over the Arctic to get there. That is the fastest way to do it. I'm not sure if I explained that well, but believe me, there are great applications of this, especially in navigation, this non-Euclidean geometry, because we live on a round Earth. Okay, I think this section, they just kind of want to introduce that to you, let it blow your mind a little bit. And you can kind of think of ways to kind of, is this Euclidean or is this non-Euclidean? And they do a little comparison and contrast. And I think that's about all, okay? All right. I hope your mind is blown.